Hi everybody, this is Brad Dyke reaching out to you to say hi. I'm trying out some new gear and stuff, and just working with some things in regards to trying to develop some new strategies and new ideas in the world of IT. One of the things I've always promoted with in regards to working with integrated technologies is that the reinventation of what we call the old equipment. Now, the competency and capability of our old hardware is quite scalable and quite functional. It can do quite a bit, but today is a different question. This time, I'm going to throw a question out to all of you out there who do listen and to say, hey, I have a challenge. This challenge is about the ability to create a new type of clustering. Now, this new type of clustering isn't going to be based on supercalculation. That's where you line up all your numerical calculators and you make them a bigger calculator by sequentially submitting equations to them in order. And I'm not also looking for a scalability bandwidth. In this particular case, because hardware is getting more functional these days, for instance, you have your NTU. So one of the principal things about today's types of clustering is to provide something that is able to compute and to scale and to compute in different classes. Now that's a key thing right there. Different class computing. Now if you have yourself a GPU, right, and you have one or two of these sitting inside your clustering, packaging, and so on, the GPU can be brought into the equation in the clear and is resourced as well as added into the equation. Now, today you can do that with a virtual engine environment in a single instance. AI can come in and say, well, I see your standard x86 processor, but I see over here a CUDA style processor. I want to use that GPU. And then in turn, it turns around and starts to use that resource to help compute, because it's got a little bit more functionality and scalability, unlike a static CPU like an Intel processor. So that's kind of like where I'm heading, except 2 steps higher. In this industry now, we have the ability of doing mathematical equation guidelines on many different levels. Network, that's the NTU, Network Processing Unit, or also referred to as an NPU. That's actually inside the NIC itself and provides you the bandwidth and those additional resources. Of course, you have the Intel processor, or the other central processing unit, may it be an AMD, and so on. And then you have, believe it or not, something known as a storage processor, right? That's a very hefty processor right there, and it's got memory and everything. And today, if you have any understanding with cryptocurrency, you can also compute storage engines to do equations and so on. So basically, any processor on board can be a classified processor. So with that being the case, a lot of people thought outside the box and said, hey, let's turn this into cryptocurrency. Let's turn that into cryptocurrency. Let's turn this into cryptocurrency. And by the way, that's most of the processor stacks inside a standard PC. Now, that's the underlying factor. You have more resources than you thought. We need an operating system that can establish a cluster at a parent controller. In other words, a static dual-paired unit that's 2 basic servers that have just a monocle amount of functionality, but they're redundant. Excuse me. They're redundant, and that's all their job is to maintain a sequential ID and to be redundant. Now, the sequential ID is the resource pool below it. So these 2 entities, with their redundancy, will share a common denominator of allocations and resourcing. So this is where everything breaks. ProxMox doesn't do this well at all. And several of the other environments don't do this as well, because they're not centralized on the hardware resources of every single box you bring to the equation. Now, that box could be a simple small form factor, like those guys you see up there on the top shelf, or they could be Raspberry Pis, or they could be, 5600s, 2600s, CPUs, stacks with RAM and disk, and so on and so on and so on. So the key thing is a ProxMox cluster can take anything, but it can only allocate so much per resource pool that joins into the pool. That's the secret sauce. That's why it's so successful, because it's going to give you everything it's got. Now, excuse me, with a operating environment like let's say Ubuntu, when you install AI on board, it goes out there and it's on a static system. So it's going to say, I see a processor that I can use to improve my AI processing. If not, I'll use the basic CPU, but it's not as fast and as furious as the class of a GPU, right? Now, that is really great, except for the fact that it won't go beyond that, which means if you ProxMox that resource, the GPU resource belongs to the cluster itself, not to an instance state. So it doesn't work. You're not going to be able to compile up those unless you actually have a GPU dedicated cluster node itself. Then at that point stage, you can throw your AI intelligence into that one or two nodes that are GPU based and have nothing to do with, a basic, booting configuration. They're just boot devices that have nothing but GPUs in them. And that's the only way you can effectively do that. But imagine what you could do if an operating system cluster platform can come in and say, give me your resources, everything, USB drives, you name it, all of that. Every piece of component functionality has a processor stack. So, obviously, when you have a tower, or you have 2Us, 4Us, and 3Us, and what other variations, or the micro manufacturer style drives up here on the top, the key thing is to understand that each one of these things have extra resources, and we're just not using them. We need a better operating clusters platform that can see all of these sub-environments. ARCs should be classified correctly in the right place. But more importantly, if you can sequentialize it on let's say a 10 gig network, right, with a 1 gig output. Now let me explain. To allow these things to interact the way they need to interact, they have to be much, much, much faster than the general result of the work they do. So, considering that most of you don't have a 1 gig pipe into the house, having a gigabit output for the services rendered by the cluster itself is more than enough than you need. So the other part of that equation, the 10 gig NICs that are connecting all of your nodes together to communicate at a much faster bus level, is there to make sure that the resources are properly going back and forth necessary to support the cluster state. So the NTUs, or the networking translation units themselves, using their NPUs, their network processing units, that are built on the NICs themselves, are able to better segment that traffic workloads and create a common pool at a 800-ish, 850 gig, 850, 8.5 gig average bandwidth. So that's going to give you everything you want. Now, granted, here we go again. We're going pyramid, but it gets better. In time, as we move into extraordinarily high amounts of RAM that is available in CPUs, including the equivalency of the GPU class, that the actual processor stack itself will contain all of those resources and plus. So the pyramid structure actually is good, because what happens is, as the operating system is being platformed on legacy, right? Legacy platforming, that's fine. There's nothing wrong with that. But it's already pre-stinted for the next generations, which will be coming over the fence, and that will be what's called high resourcing processing units. In other words, resources much higher than today's cache of L1, L2, L3, and or secondary style RAM resources that could act as boot drives and so on and so on. It's coming, it's just not quite here yet. With that being said, the other value of this operating system cluster platform is that it brings all the other devices in your system to bear. What does that mean? Who knows? What can somebody do with 8,000, or not 8,000? Let's say 128 USB device configuration sets. So let's say you got 10 nodes, so that would be a little over 1,000 USB resources. What can we do with it, right? How do we use storage mode calculation, like it's used in storage cryptocurrency, by the way, to add to the equation of the CPU, the GPU, and also the MPU, the network processing units? They all can be used. Why not? Take advantage of it. The other values that would be excellent is to be able to reach out into the other class processors that exist. Why not? I mean, they're out there. We know what they can do, and they receive instructions. I mean, it makes perfect sense. I mean, the Quadro Pro, why not? It's still basically a graphics card, for the most part. Why not? I mean, you just load up all the slots on your motherboard with processing units, and they turn around and they become resources for the internal motherboard to add to the greater resource pool. Now, this makes more sense to me, because as we go to PDs, or personal devices, and those devices could be as small as something like this, with a small display screen on it, and it gives you information because you're connected to somewhere in the internet. These other platforms, like you see back here, can really turn their resources into something very impressive. Now, the one reality of the fact is, if we go down this avenue, you're going to have what is known as a cluster latency effect. The more you add to your cluster, the inevitable downcurving effect which you'll have. Now, what do I mean by that? Well, in the industry of storage, bandwidth, compute powers, and so on, we have what's called the downward curve syndrome, which basically means is we're going to have success, and then we plateau, even though we're still adding resources, but now the interactions of the resources begin to bring down that overall success to a lower, more latency burden-based overhead. In other words, not as fast, not as functional. So we want to get up to the curve area where it's best at, keep it there, and avoid the downward curve. So cluster latency effect is going to be real. And every time you bring in another processor, maybe an MPU or an SPU or a GPU or a CPU, the basic line is those each will come into the megahertz cycle process effect, creating what we call the effect of latency. Put in additional devices, including storage and so on, that latency gets longer and longer. So there is a fine line of balance that needs to happen, unless we can develop a faster bus. Now, that's a problem because you don't have consistency with the processors. So that can't be the driving force. What has to be the driving force, and here we go, is the common bus. And in this case, the common bus is a 10 gig pipe that loops all the devices together. Now, there's one last disadvantage. Raspberry Pis, as neat as they are, don't have the capacity of a 10 gig connection. Now, yeah, you could technically put in a USB to a 10 gig adapter interface if you wanted to. Why? So now this goes to the next part. A wise cluster platform is one that can work in tiers. And by working in tiers, you have what you call the test environment, you have what's called a quality environment, and then you have what's called a production environment. So the cluster environment has to be able to say, hey, you only rank here, so you're at test level because you're not fast enough, and you can do so many resources, but that's optimal for what you can do. And then you have a mid-size level, and it does the same thing for what it could do at the mid-size level. And then you have the high bore, okay, kick butt, here's my answer, bandwidth, and it's the high end of the environment. And that would be dictated by the classes of the devices you bring to the table. So if you have a Raspberry Pi, an Aerial, and a couple of x86, dual processor stacks, well, Pis are low, Aerials are mid because they're the 2.5 gig connections, and of course the 10 gig connections on the two x86s. hence tiering. Now, it changes again if you have a quad processor with 2 or 3 10 gig pipes for adaptive load balancing, which will get you a lot higher bandwidth. That's your new high, and you've got quads or dually CPUs. Those are your mids, and then the single CPUs, and then your Raspberry Pis and Aerials would be part of the test and lower. And that would give you that automatic intelligence that would say, by classifying you guys in the right groups, we can use those bandwidth channels more effectively. Well, this is just me talking, I'm opening up saying, I need this, I want this. I put the challenge out there. Is there anyone out there who can say, I can maybe do this? We can look how ProxMox started, or Nutanix, or Terac, or VMware, and OpenBox, and all those kind of environments, and others, open source, of course, VirtualBox, and so on, can bring to bear a resource and an ability to augment it into this new generation, and then that basically decrees very easy integration with a very nonsensical client kind of interface that isn't complicated and doesn't require much to config. And why not? I mean, it's a great idea. So with that being said, the last part of that great idea is its nature. Now, this is a little bit on the hard part. When you're building your parent entity, you would run the installation of the cluster software in what's called the parent directory, or the parent node. The parent node would be 1 or 2 optimal, that would act as the controller. In other words, what we call the cluster node controller, if you think of Beowulf and some of the older environments. The controller is the guy who kind of keeps everything in sync. It's very much like a RAM card or something like that. It's got a small microchip on it, it's this controller chip, and then it handles all the transactions of the environment. And that's basically what this clustering really is. It's kind of like a RAM card. It's got a controller chip set, and it's got all these DIMMs or DIPs or whatever you have. It's an old card, by the way. You have to go back about 10 years ago. And then it would just kind of coordinate all the traffic loads, and each buffer would act as a capacity. So that's what you would do. You would install the single operating cluster agent, which would be installed on the 2 pieces of hardware recommended. Then you run the same program again, but this time you add it as a support node. So either you run the software, iOS environment or image, as a parent installation, or you run it as a support installation. Now, the support installation is the one that can go on as small as a Raspberry Pi, or as big as a quadrilateral dual 3 or 10 or 100 gigabit bandwidth device. All it needs is the basic core CPU configurations that are normal today anyways. And then it will go out there, and it has the discovery algorithms that will go out there and say, what can I use that you have that are processors? MPUs, storage processing units, GPUs, and so on and so on. Now, this would motivate us to put better GPUs in our bigger towers, because those guys would be excellent for AI intelligence. In other words, you want to build an AI environment, and I've been doing that lately because it's time to get comfortable with that process. And I've gone out there and I've set this environment up so that I can do that. And I'll tell you what, it's 2 seconds versus 15 seconds if you don't have a GPU on board that's worthy. So with that being said, the AI intelligence functionality is how you make it. So that makes it really valuable. So like I said, the 2 parent nodes don't do any of this at all. They are dedicated resources with a block of memory, a processor, dual power supplies. They're your boss. They own it all below. But below is where all the real fun happens. There you can build your virtual instances out. There you can add your subject and services recalls. There you can add additional things like rendering tools and so on and so on. And all it does basically is help you get to where you want to be by using more and more and more of the hardware that you can get into the equation. So you could throw in 15 or 20 Pis, some aerials, like 4 or 5 or 10 aerials. Those 4070s up there on the top shelf. They can all join into the parenting cluster model, and offer their resources to the the overall functionality. And with that being said, I think that we are at a point where we are close to being able to do that now. And now it's just really one of you guys and gals who are smart enough to go back into the command kernel of a standard Linux environment and think, well, how do we want to build this out? How do we want it to work? This is more logical, and I think things, even CD-ROM drives, have value because you can populate those and create what's called a CD archive. We used to make those 15 years ago, 20 years ago, and you know what? CD-ROMs are coming back. They are not going to be like you think they are now, and they'll have a different role, but the strategy still makes sense, and the functional protocol is still the same. So why not? What the heck? Can't hurt. Media converters. In other words, you have multiple formats where you can take media inputs. What do I mean? Well, here's an example right here. If you look right there, you'll see that you have different kinds of media interfaces that exist. And you've got extra USB ports. So I'm the one in the room saying, hey, you got him. Why not use them? What can they do? Why not? What if you put USB memory sticks into all of the USB ports, and they're 16 gigs each or 32 gigs each, and then it can create what's called a commonality caching buffer using USB drives. Why not? Because it's localized and accessible by all the nodes. All they have to do is have it on their high-speed bandwidth to access it. So those are just ideas. It's just something that which can be of value, and ProxMox is a pretty decent tool. Nutanix, same thing. They're all basically the same cookie cutter. It's time to take the next step. What's beyond, today's resources that could come in and just really drive the ship, pick up all those extra resources you have in those chassis. Use them, abuse them. Bring your clusters up to even greater capacity just by using the hardware more intelligently through your software. Something to think about. Well, this is Brad Dyke. This is my textual, intellectual video that I plan to do for this week, and I'm going to let you guys go. God bless, and have a great week. Take care.